Hello and welcome everyone. My name is Juan Gandarias and I am a postdoctoral researcher at the Human Robot Interfaces and Physical Interaction Group at Istituto Italiano di Tecnologia. This presentation is part of the workshop on floating-based robots in manufacturing and logistic operation at Humanoids 2020. So in this talk, I would like to present our recent advances about active supernumerary body for physical robotic assistant in industrial operations. Existing collaborative technologies can be categorized as these three that you can see in these videos, which are exoskeletons, supernumerary limbs, and collaborative robots or mobile collaborative robots. Exoskeleton can have unintended negative consequences such as reduced flexibility, which can lead to new sources of musculoskeletal disorder or accidents. And also they can reduce the mobility of the user, which may also produce discomfort on the workers. On the other hand, supernumerary limbs, which can augment human capabilities, imply fewer mobility limitations to the users compared to exoskeleton. But since the user carry the extra limbs, they can also experience fatigue in the long term. In fact, it has been demonstrated that the workers prioritize greater dexterity and lighter weight. The last collaborative technology refers to cobot, which opens up a new horizon of opportunities for this, but also for other applications such as healthcare or disaster response. They can also contribute to better ergonomics and comfort to the human counterparts. In order to face these issues, we proposed the MOCA-MAN concept. MOCA-MAN is actually a robotic framework that aims to exploit the configuration potential of a mobile collaborative robotic assistant that we call MOCA, that you can see here at the right, to merge the features and advantages of cobots and supernumerary limbs. So basically, the idea is to create an assistant robot that can not only function autonomously or in close proximity to humans, but also that can be physically coupled to the human counterpart as a supernumerary robotic body. This way, the user doesn't have to carry the weight of the supernumerary limb and can only attach to the robot when it's needed. One main advantage is that the mobility of the worker is not compromised, as in the case of exoskeleton, which means that the attachment between the robot and the human is made basically at the hand of the worker and not on all of the arm. Another advantage of using this kind of technology is that when the robot is not being used for conjoined human-robot action, it can be used as a mobile collaborative robot that can perform a different work. We believe that this kind of system can not only contribute to the user's comfort, increasing productivity, but also to reduce equipment weight and setup times. So in this slide, you can see our first approach, our first solution to this problem. So first, we designed and developed this interface to operate the robot. This interface is based on two different parts. So on the left-hand video, you can see the Mayo armband, which is basically a set of EMG sensors that can recognize different hand gestures. And by using this interface, the human can send different commands to the robot in order to change different parameters of the controller or the behavior, as we will see later. On the right hand of the slide, you can see the admittance interface, which is basically formed by a force torque sensor and a magnetic clamp. And as you can see in this clip, the human can attach or detach to the robot using this clamp. The force torque sensor is used to map human forces into desired end effector velocity through this admittance formulation. So this way we can operate the robot motion locally. Before showing the MOCA-MAN framework, I would like to talk about the whole body controller of the MOCA. This robot integrates a Cartesian impedance controller. So here you can see some equation that defines the impedance behavior of the robot. But I don't want to enter too much into the details, but I will just like to describe peculiarities of the behavior. So this first equation defines the coupled whole body dynamics of the arm and the base. So one particular thing I would like to highlight is this weighting matrix that we can see here, which basically allows us to define motion priorities. It means that we can give more priority to the motion of the arm or to the motion of the base. So in this video, we can see that both the arm and the base are moving equally, which means that the motion priority, which is given by these two parameters, is set to equal. The correct definition of these priorities is useful to develop different kind of tasks that may require different motion modalities. So as you can see in this video on the right, the robot can exploit this feature and change these weights online to perform these three operations, which consist basically of approaching the door in locomotion mode, grasp the handle in manipulation mode, and finally open the door in loco manipulation mode. And also the desired impedance behavior is defined by these two equations, in which the stiffness and damping matrices can also be changed online based on the task requirements. In this slide, you can see the whole framework integration. Basically, the framework has two modes, the autonomous and the conjoined mode. So in the first one, the robot carries out a task according to an autonomous motion planner, while in the second one, the human is physically coupled to the robot to use it as a supernumerary body and carry out conjoined human-robot action. You can also see here in these circles the gesture that the myosensor uses to command different actions to the robot. So for example, through the double tap, the user can change between autonomous and conjoined modes. With the fist, the user can send a command to open or close the soft hand. And with the wave motion, the human can change the weight parameters of the whole body controller to give higher priority to locomotion or manipulation modes. Also, you can see here the whole body impedance controller and the human-robot admittance interface, which is used to map the interaction forces exerted by the human into the desired velocities and position of the end effector. So in this video, you can see a demonstration of the MOCA-MAN framework. So first, through a gesture, the user calls MOCA, which moves towards the human in autonomous mode, and then the user attaches to the interface through the magnetic clamp. Using the wave gesture, the user changes to locomotion mode and moves towards the case. So now the user changes to manipulation mode again, and with the first gesture, the fist gesture, the robot grasps the case. Once the lifting phase is done, the user changes again to locomotion mode and moves towards the target position. And during all this carrying phase of the task, the human is not carrying any weight, reducing the effort needed to do this lifting and carrying task. Finally, in the placing phase, MOCA enters again in manipulation mode, and the user commands the robot to open the gripper, placing the case on the table. So once the whole task is complete, the user can easily detach to the interface. So this work proposed the first approach to supernumerary mobile manipulator for physical assistant. The framework demonstrated local manipulation capability thanks to the whole body impedance controller. This work also proved that the human partner's effort is reduced thanks to the physical admittance of the supernumerary robot. And in comparison with other existing technologies, one of the main advantages is that the user doesn't have to carry extra weight, as in the case of the supernumerary limbs, and also that the mobility of the user is not compromised by the robotic assistant, as in the case of exoskeleton. However, still there are some limitations, as this is the first approach to this problem, which are basically that the current platform has a limited payload, which is not suitable for several industrial tasks. The proposed interface might not be practical for some scenarios in which robustness is a must, as the interface needs to interpret human gestures, and some of them can be misunderstood, which in some occasions can lead to accidents in the workplace. Moreover, the assistant features and that the framework provides to the worker are limited to the carry of the weight. The potential of the proposed solution hasn't been exploited yet. So we just said that one of the limitations of the presented interface is that it may not be practical for industrial applications. So recently we developed this new interface, which has a simplistic design that promotes usability and robustness and eases the human-robot coupling. This interface was 3D printed and it's formed by the components of this figure. Basically, the interface is formed by a main handler connected to a force torque sensor. So this way the human can simply grasp the interface and locally operate the robot. Another feature is that the myosensor has been replaced by a button interface with a microcontroller that takes human inputs and communicates with the robot via the serial port. So the buttons board has 4 buttons that can be used to change the local manipulation mode of the robot, or for opening and closing the gripper, for example. So the goal of this interface is to provide a more comfortable human-robot coupling that can be operated with one hand only, and that can be easily reprogrammed based on the requirements of the user of the task. So in this video, you can see a use case of the proposed interface. As I said, the user just can grasp the interface with one hand, and through the buttons board can change different parameters of the robot controller. As explained in the word before, the human can change between locomotion and manipulation modes, or can open and close the gripper, for example. And also, as you can see now, thanks to the comfortable coupling, the user can easily and precisely perform typical industrial tasks, such as, for example, the painting task shown in this part of the video. So, in order to validate the performance of this new interface, we ask usability-related questions to 12 subjects, 6 men and 6 women. So in this figure, you can see the results of the questionnaire, and the outcomes of this work is that the new interface presents an industrial-like design, which is comfortable and can be operated with one hand only. And according to subject experience, it's not complex and it's easy to use. And they also claim that the functions of the interface are well integrated. But still, there are some limitations, or let's say some potential improvements to do in future work. So basically, the interface has some limited features, which mean that there are not many controller parameters that can be tuned with the buttons, and this also limited the flexibility and the configurability of different task requirements. And also, right now, the interface that doesn't consider the user preferences and it will be interesting to work on an interface that, based on the user, can autonomously change some parameters of the robot controller according to past user preferences. So now let me talk about our most recent work, which is a high-payload supernumerary robot assistant that you can see in this picture. So here you can see some feature of this robot. The robot and also the system are based on the MOCA-MAN concept also. As you can see in the picture, my colleague Alberto is using the same interface I described before. The only difference is that in this case, the platform integrates a velocity-based controller arm that has a high payload up to 16 kilograms, but as well as MOCA, thanks to a whole body controller that I will explain later, because it's a little bit different than the one I presented before. This platform includes some local manipulation capabilities as well as MOCA. So basically, with respect to the previous one, this one presents higher potential for industrial application, especially for those that requires high payloads. So in this case, let me explain first the framework before defining the controller of the robot. So in this figure, we can see the framework categorized by 4 different colors. So the blue refers to the robot part, the purple is related to the human interaction, the green refers to the interface, and finally the orange refers to the controller. So basically, this framework is more or less the same as the MOCA-MAN presented before, but as I said, this one includes the new interface. So in this case, instead of using the Mayo sensor, the user can send commands to the robot or the controller through the 4 buttons interface. Like, for example, in this case, activate or deactivate admittance interface, change between local manipulation modes, change the admittance behavior, or let's say sensibility, and also open or close the gripper. Let me explain the main difference between this platform and MOCA, which is basically the controller. As I said before, this platform also includes an admittance controller to map human forces into the side effector position and velocity, which we also had in MOCA. But in this case, the platform integrates a velocity-based robotic arm, so we can directly send desired torques to the robot. So this means that the platform doesn't include this Cartesian impedance behavior. This aspect has some advantages in terms of accuracy, but some disadvantages in terms of safety. But in any case, the robot is still collaborative and can work in close proximity to humans, and as it will stop if an unexpected collision is detected. Let me just skip some maths and some equation of the controller a little bit, and let me just explain a couple of interesting features of the proposed application. So the whole body controller solves an inverse differential kinematics problem with secondary tasks using a hierarchical quadratic program formulation. The controller considers a primary task responsible to track the effector position and velocities given by the admittance controller. And this task also considers the manipulability of the robot through this parameter K. This parameter is tuned online as a function of the manipulability index, so that the relative importance of minimizing the joint velocity with respect to tracking the desired effector motion is increased when the robot is close to a singularity. The controller also includes a secondary task that tries to keep the preferred robot configuration of the user. But let me explain it better with a video demonstration. So in this video, you can see the functionalities of the controller. So at the beginning, you can see my colleague Alberto and that the robot is in a certain configuration. Then the user activates the admittance controller and changes the configuration of the robot in the manipulation mode and to a specific preferred configuration that the robot keeps thanks to the secondary task of the controller. Then the operator changes the mode into locomotion to go towards the gate, which in this case weighs 10 kilograms. And again, using the interface, the operator can change to the manipulation mode, grasp the object. Once the object is grabbed, the operator changes again to the locomotion mode and goes towards the target position. So here you can see some plots as a result of this experiment. The plot at the top shows the interaction forces applied by the human, while the second plot shows the desired and actual linear velocities of the end effector. We can see the good performance of the controller when tracking the desired linear velocities. And the two other plots show the torques exerted by the human and the desired and actual angular velocities of the end effector, which the controller is also capable to track. Finally, we carried out this overhead drilling task, which is a very common task in industry and can cause severe accidents and some musculoskeletal disorders due to the need of holding a heavy object for long time periods. So we carried out this experiment with and without the robot in order to measure different metrics, to carry out some statistical tests to understand the usability of these proposed technologies for this kind of task. So in this experiment, the tool weighs 5 kilograms, which is quite heavy for a human. And as you can see in this figure, the human operator also wears surface EMG sensors to measure the muscular activity. Then we define a task path in order to count the number of holds that the user can do when has the assistance of the robot or when doing the task by themselves. When the subject did the task with the robot, they did all the 20 holds that were proposed. But when they weren't assist, only a few of them were able to do all the holds, and many of them were not able to do even the half of the holds. However, the time to do the task when using the robot is a little bit higher than when not using the robot. But we think that this could also be caused because the subjects are not used to this kind of tool. So maybe with some training, they will learn how to use this tool more efficiently. We also ask the users for mental workload, which according to their perception is reduced when they are using the robot. So here we have some results that can share some light on the usability of this proposed technology. So on the left-hand figure, we can see the results of the usability study in which the subjects carry out the NASA TLX questionnaire. And through this questionnaire, they express their subjective perception on different aspects of the experiment when doing the task with the robot, which are the results on the left, and without the robot, which are the ones on the right. So in general, and according to their perception, all of these indices, which are the mental, physical, and time demanding, the performance, the effort, and the frustration, are always better when performing the task with the robot assistant. Of course, some of them present some more more statistical significance, as for example, the physical demanding, the effort, and the frustration. While on the right-hand figure, we can see the EMG results. And in this case, we measure the muscular activity when using the robot and when not using the robot for the anterior and posterior deltoid, the biceps, and the triceps. So here we can see that both average and maximum activity are reduced in the robot case, and also that the anterior and posterior deltoid, which are the muscles that are more significant for this kind of tasks, present the highest reduction. So in conclusion, in this talk, I presented the first approaches on supernumerary mobile manipulators for physical assistance in industrial operations. I presented two different robotic platforms, one with torque-based control and the other with velocity-based control manipulators. They respective two different whole body controllers. Besides, I also describe an admittance physical interface that allows us to locally operate these two kind of robotic platforms. I described a usability study for the application and experimentation of these platforms to carry and lifting and overhead drilling tasks, which are very common tasks in industrial operations. And overall, we can conclude that this technology can help to reduce worker effort, improve the flexibility without compromising the motion of the worker. And last but not least, I would like to share with you the future perspective of these works. So overall, we think that this technology can be improved in terms of the interface, which we believe that it cost might be reduced if we find a way of not using the force torque sensor to operate the robot. Another potential improvement is to make it wireless so that it can be shared or used for different kind of industrial application in the industry. But to achieve this goal, some functionalities must be enhanced, for example, by taking into account the user preferences or using the interface to teach the robot how to do a certain repetitive task. We also believe that this technology can provide more advanced assistance to the human. So, for example, what about using learning techniques to improve the assistant? Another way of improving is by enhancing the assistant in terms of shared autonomy and guidance, considering haptic communication between the robot and the operator. We would also like to carry out a comparison study to better understand the difference from task performance and user preferences with respect to exoskeleton and supernumerary limbs. That was all. I will be very happy to discuss about these topics in the live session of the workshop. I'm also happy to answer any question you may have. Thank you very much.